Can you see this screen?
Yeah.
Okay. So here's where we left off on Wednesday. And just as a reminder of what we were doing, we were going through decision trees. And this is the, maybe I should back up to refresh everyone's memory. But we were looking at deciding on which route in the weather example that we were considering. Everyone remember that weather example? Jeremiah, Katie? Okay. And there were a number of attributes. There were 4 attributes to try to determine the final class of play or no play. The attributes being outlook, temperature, humidity, and wind. And so we're trying to decide, we're going to use entropy as our measure of impurity or measure of information. And basically the idea, it's the information that we can still obtain from the system. So that's how this works, and we're going to use entropy as our measure here, right? We outlined 3 different measures. We outlined entropy, the Gini index, as well as the classification error. And I mentioned that they're really consistent with each other. And so I want to go through this example, pick up where we left off again. So when we look at outlook as the root, the cord. When you look at outlook as the root, there were 3 different, so in fact, maybe I should back up here. There were the 3 different branches, right? After outlook, we can then go sunny. The 3 different classes were sunny, overcast, and rainy. And notice in sunny we had 2 yeses and 3 nos, so 2, 3. Overcast was 4, 0, and rainy was 3, 2. And we left off here. We're going to try to find the information that we can, I went too far. So if we use outlook as root, we have these 3 different branches. We have the information 2, 3. And the question came up, how do we actually calculate that? And that goes back to the entropy calculations. Notice we had 2 yes instances and 3 no instances. And so what that means is the amount of information to be gained there is probability 0.4 times the log of 0.4. And remember, the log is base 2, plus the log of 0.6, which is 3/5, times the log of 0.6. And that's where you got that 0.971 bits for that one branch, for that one class, sunny class. And then for the, I think it was it, what was the second branch? Overcast. There it was 4 yeses and 0 nos. So that's already decided, basically. It's a yes. So there is no more branching that you can do there. So it's completely determined. And so your information there ends up being 0, which is 1 log 1 plus 0. So, and then similarly, info of the last branch, rainy was 3, 2. Again, by symmetry was 0.971. So picking up from here, we then calculate the total information of the 3 branches, weighting each branch by the number of instances. So here we have 5/14 times the 0.971 plus 4/14 times 0 plus 5/14 times 0.971. So what that says is using Outlook as my root node, then we get 0.693 units left to that is available to learn. Okay. So where we go from this, we similarly can calculate the initial information that we had. There were the initial information, we have 14 instances. Of those, 9 were yes and 5 were no. Again, use entropy to calculate that information, and you'll end up with 0.940 bits. And what we're interested in is how much we gained by using Outlook as my root. And in that's just the difference between the initial amount to gain minus what's left afterwards. In that case, we've gained 0.247 bits of information. If you do similar calculations with the other three nodes, the other 3 possible attributes for your parent node, or your root node, you would get a similar calculation, would give you a gain using temperature as your root node of only 0.029 bits. Humidity gives you a gain of 0.152, and windy gives you a smaller gain, 0.048 bits. So from this calculation, it seems that it would be easy to use, the best choice would be to use Outlook as the root for splitting. It's going to give you the most information gain as you go forward.
Okay.
Okay? Now you do have to, there's a but down at the bottom there, right? But dot dot dot.
Dot, dot.
Okay, 6 dots. Because it's sometimes not quite that straightforward, and that's why I want to continue with this example. So what can go wrong? So here I've gone through the same example. Notice we still have Outlook, temperature, humidity, windy as our 4 attributes, as well as play, but I've added another attribute to this table. We don't know what until we start looking at the data and analyzing the data, we don't know what all the attributes are really going to be, right? So here I've added an ID code to all of the data here, okay? And let's see what happens if we now branch on the ID code, right? Well, here would be the picture, and I didn't draw the whole thing, right? If I branch on the ID code, we have one branch going to A with a final single decision, 100% knowledge there, right? Same thing with B, C, D, E, F, G, all the way up to N, the 14 cases. And if we calculated our total final information, well, because it's completely determined at that point, we know if you classify off of your root ID, you've classified everything right away. There's no more information to be gained. But that's nonsense, right? Because, and I'm going to play into this, in terms of data mining, it's not just that you want to classify everything, and the ID is just giving you a unique output. If it's A, it's no. If it's B, it's no, right? It's not telling you any information, especially, remember, what we are interested in is using the model that we gain to try to determine information that we have yet to see, right? So if I added another instance in here, O, how am I going to classify that? We haven't really built a model Does that make some sense? You look confused, Pablo.
I think I'm following.
It's meaningless. The gain ratio is the info of 111, 14 ones, 1/14th log, 1/14, 3.807, which is larger than anything else we've seen. So what we're going to do, the gain here, I went a step ahead. The gain ends up going from 0.940 all the way down to 0. It's much larger than any of the other gains. But as I say, it's a meaningless attribute to split over. So a couple ways we can deal with this. One is using the gain ratio. And that's where I calculate the information value of the final split. Basically, what the problem is, it's splitting it over every single instance, right? It's, I like to use the example, and we'll have some other ways of thinking about this, of a model of the physical universe by knowing the location and motion of every single atom in the physical universe. It doesn't really tell you about the physical universe, right? It's so much information, and B, how do you use that to predict things versus Newton's or Einstein's laws of motion, which are very simple descriptions. They may not, they're going to be approximations for a lot of things, but they usually work. If you try to make a model using the position and location of everything, then you get another particular piece. You don't know what's going to happen with that. So we're going to introduce this idea of the gain ratio. So we calculated the information, we got 3.807, and what I'm going to do now is take my gain, divide by that information of the split. And notice I have 14 ones there. And the idea here is it gives precedence, or it gives more weight to smaller splits versus larger splits. So the issue here is I'm splitting 14 versus into 2 or 3 classes. I'm splitting it right away into 14 classes. And so it's trying to give a lower weight to those larger splits. If you do compare it, it's still not perfect. We still have a larger gain ratio for the ID code than for the other nodes. But notice it went from 3.8, or what, no, 0.940, right, down to 0.247. And so you would want to use some other methods to really eliminate that ID code as a branch. Usually some heuristic or ad hoc methods to first eliminate nonsense branches like that.
Because, well, the lower the gain, sorry.
So the higher the gain, the better the root. The better that is for a splitting. And remember, then we would proceed with this. So forgetting the ID code, now suppose we did split over the outlook. So now you have 3 branches, right? You've got 3 classes, the sunny, overcast, and rainy. Now, I mentioned at the beginning, last class, you're now going to do this process recursively. So now I'm going to I'll branch on outlook, and now we're going to do the same calculation for out. So now we're going to repeat the process that we just finished over the other attributes, temperature, humidity, and wind, to select the next attributes over which to split.
Like you're splitting up outlook, finding which one of those nodes.
It's a greedy algorithm, right? We're finding the most information we can gain from the first step. And then we're gonna repeat and find, okay, now which split will give us the most information next?
Yeah.
Is that,
Yeah.
okay. So, some characteristics in general about decision trees, they're easy to understand, right? Here's some nice properties. It's similar to human decision process, okay? I have these four, let's split in one direction and then split again and try to get as much information as we can. It deals, we saw it in the weather example, we had both discrete as well as continuous attributes. The temperature was continuous. Some of the others were discrete. Was it sunny? Was it overcast? Was it rainy? It's fairly simple. Non-parametric, we don't have to really worry about setting parameters to try to come to decisions. We don't make any decisions about what sorts of probability distributions are underlying the classifying algorithm. We'll see some different cases where we do have to worry about this as we proceed forward, about the probability distribution types. It is an NP complete, which means in particular it's an NP hard problem. Basically, we saw that early on, that the number, NP is non-polynomial time, the number of trees for a large number of attributes grows very rapidly. I mean, it grows, factorially? If you try to determine all the possible numbers of trees, right? Because in our example, we had 4 attributes for our first root node, and then once you choose one of those, you have 3 underneath, and then 2, and then 1. So that's factorially in terms of the number of attributes. So that's why you want some sort of quick algorithm to help you choose the root node to begin with. You don't want to search over all the trees at the very beginning. So you're going to do a greedy search right away to get the first node that gives you the most information. It doesn't necessarily guarantee you'll have the optimal tree in the end.
How would you determine that?
Well, I mean, one way would be to look at all possible 24 trees, but
Yeah.
if you have 100 attributes, good luck with that.
Yeah. So to kind of take a chance out.
Right. I mean, are you familiar with, say, something like a traveling salesman problem? I mean, it grows in a similar fashion, right?
Okay.
But there are algorithms that seem to work well. So, this is an example of that. The algorithms that we have, for example, the one I outlined for you, we'll look at some other algorithms for classification, not based on decision trees, but decision trees are fairly computationally inexpensive. You saw we did it by hand here. It didn't take a lot of calculations. I mean, you can do it even with 100 attributes. You can do p log n for 100 different branches and see what comes of it. The decision boundaries are basically where those trees end up breaking the information up into different pieces. And so those can become very complex very quickly, and they're represented through the decision trees. And as usual, the bottom bullet point here, overfitting can be a problem, which leads us to the next topic I really want to discuss today, which is model overfitting. So before, I'm gonna, for those here, I'm gonna block the screen, right? So when I say model under overfitting, what comes to mind?
A learning
Everyone in Daytona Beach sees the screen, but here, pardon?
A learning algorithm said to overfit relative to a simpler
Oh.
one. It's more accurate than fitting.
I guess I can't block the screen, right? Okay, so
Oh, spot on.
it fits the known data, right? Yeah.
I was just gonna say, trying to fit as much data into like the algorithm as you can, and then you end up with more data than you actually need. Is that kind of?
Okay. Well, the idea, I mean, in essence, that the example we saw with the ID code, right? Remember, we're gonna try using a training set and then a testing set. And ultimately, our goal is not to do 100% on the training set, but our goal is to predict future unknown data better, right? So in that ID code example, yeah, we fit our data perfectly, but it has no idea how to fit something that it's never seen before. Because now you have a new class, what's the ID code? It's O,
Okay.
right? And where does that fit? Well, it's gonna fit in its own new category. Well, is it a yes or is it a no? It hasn't really learned any information to make that decision. It's not looking at the individual, characteristics of what's going on. Is it sunny? Is it overcast? Is it windy? Is it humid or not? How is it going to make a decision? All it's looking at is class O.
So is it like oversimplifying?
It's the exact opposite of that. You're making your model so complex, in essence, that universe, atoms in the universe kind of thing, that here's a new atom, what's happening with that one? You've determined everything, but it has no predictive power.
Okay.
Okay?
So
Yeah,
it's like you know everything, you just don't know what's happening next.
you know everything that in your training set, so to speak. But that training, that your model that you've developed, in that particular instance, it's not just overfitting. In that particular instance, it actually can't do anything with a new class, because it doesn't even have any information to work with. Okay. But in general, the idea is, yeah, you can fit things very closely, but have you generated a robust model that does well on new unknown data versus the data that it's very specific to that data that you fed it in. And even then, you have to, even if an example of that came across, I'm trying to remember the exact details, but was some picture recognition, and I think it had to do with tanks. And they fed all these pictures, these images in to an algorithm, and they didn't know what the algorithm was actually doing at the time. And it did really, really well on the training corpus. But it didn't do that well on the actual test. And what ended up happening, was that I don't know if the pictures were mixed, some of the pictures are black and white, or they were finding gray objects in the pictures as identifying as the tanks, rather than the shape or picture of the actual tanks.
Hmm.
So, in other words, it was using the training set, and it ended up training on something that you didn't want it to train on. And so when you actually ran the test set through, it found something other than what you were looking for. And so the test set performance was not good. So it's tricky stuff. Past experience can be divided into two groups: information that's relevant for the future, which is really what we're interested in, and then irrelevant information, which we sometimes call noise. And the trick is the ID code example is irrelevant information because it's not even really information. I mean, it's completely specifying the training class, but it has no predictive power. Where does class O go? Is it going to, do you want to say play or not play? You don't have, how can the instances A through N, those ID codes, give you that information?
So, what it seems to me is that this becomes a problem if there are outcomes that we do not expect, right? So,
Well,
if there's an unknown outcome,
right?
then we wouldn't be able to predict that using something like this, right?
Right.
If we know,
So-
if we know all of the events that could happen, would this be a problem?
I'm not sure what exactly you mean.
Well, I'm trying to think in terms of probability, right? Each event, you know, multiple events in a set, I guess.
Right?
So if you know every event that can happen, then overfitting wouldn't be an issue, right? But it's just that the unknown event we cannot predict.
Right.
Okay, so we want something that can take in information and give us something else, right? Not
Take in
just-
information and is basically it's flexible enough to kind of determine things based on character. I mean, you're gonna try to come up with a model. I mean, that's your goal. And use that model, I'm not sure if I'm answering your question, but to make predictions for information you've yet to see. If you think of a classic example is past performance in stock markets, and how can you analyze that and perhaps see patterns that can be useful moving forward. But just knowing the particular instances of movements, right? If this, and this, and everything completely specified, then it goes up. Whereas in this case, it goes down. Now you've overfit. If you've specified it, specified everything, because now you see something you've not seen before. Your system hasn't generalized those instances to some sort of simpler pattern, and I'm going to come back to that.
Okay.
Does that help answer?
Yeah.
In fact, here it is. So this generally happens, these problems of overfitting generally happen when your model that you develop is excessively complex and overspecifies the instances. And it can, part of the problem is it exaggerates minor fluctuations in the data. So let's take a look at that. What are some causes of overfitting? Noise, noisy data. Lack of data. If you only have 2 data points, to determine what the weather's going to be like tomorrow, then you really can't generalize from the current conditions. You've had two setups before, two conditions that you were able to determine before. One ended up sunny, the other ended up rainy. Right, but there's a lot more subtleties involved. And so if you only have a few data points, it's really hard to predict things using that data moving forward. And there's a problem when, basically again, as you increase the number of comparisons, it becomes more likely that you will see something. You'll see a difference. So that's called the, can't remember. Multiple comparison problem. And basically it's a problem in probability. It's your infinite number of monkeys. If they type long enough, you'll get the works of Shakespeare. Example, right? You don't need an infinite number, but if you get a huge number, eventually, chances are you're going to see something, whether it's valid or not. And it's, again, related, I can't overemphasize this, to model complexity. Which brings us to a few different approaches to solving the problem. And some of you here in Alamosa may have heard me talk about Occam's razor. Yes? Okay. Occam's razor. It's named for William of Occam, circa 1287 to 1347. He was a medieval philosopher. And the idea of the razor, the term razor, relates to distinguishing between two different cases by shaving away unnecessary assumptions or cutting apart two similar, shaving the difference, basically, two similar conclusions. The idea is simply expressed, and I've got a couple of quotes coming up, but simpler explanations are, other things being equal, are generally better than more complex ones. So you can describe things in simple terms, relatively fully, that gets the idea across as better than trying to over describe them. And it's a heuristic, so it's not written in, I guess, stone, so to speak. So a couple of phrases of this. One by Newton, who said, "We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Therefore, to the same natural effects, we must, so far as possible, assign the same causes." Or Einstein, "It can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender the adequate representation of a single datum of experience." That last one you may have heard paraphrased, as I have down here, as everything should be kept as simple as possible, but no simpler than necessary. Get the idea, fully explain everything, but in as simple of terms as possible. It's a heuristic, but I mean, that's one way to avoid model overfitting, and leads us to a particular implementation for decision trees is called the minimum description length. And we're going to go through an example of this. You can see it on. Whoops, looks like I have a couple typos there, but the basic idea here is the best hypothesis is that which leads to the best compression, the most simplified model, the one that's able to be reduced into as simple a form as possible. That's the idea of best compression. And the idea here is that the total cost that should be an equal to should be equal to the cost of the tree. How did I want that? It's the cost of the tree and the data, and it's given by the cost of the tree plus the cost of the data given that tree. So it breaks it up into two parts. So your total cost is the cost of your decision tree and any errors in your measurements, right? So the data goes in there. So it's the cost of the tree plus the cost of your particular data given the tree that you developed. Yeah, we're going to go through an example. You had a question?
It just says the cost of the tree and data, and then cost of data and the tree. I didn't know.
Well, this should have been just basically a hyphen. That's not a subtraction there.
Oh.
So,
Okay, never mind.
yeah. So that first, it's not a total cost minus. It's total cost. Think of it, there should be a semicolon there.
Okay.
So here's an example, and this is actually from the TAN book. It's problem number 9, which is not on your homework, but booyah. So here I've generated 2 trees, right? The first tree, we have data with 16 binary attributes. And 3 classes, C1, C2, and C3. And so we've got these 2 trees. The first tree splits. 1 gives you class C1, and here the second one splits in another direction, which then splits into 2 and 3, right? And you can see how the second one, it's a more complex decision tree. But down at the bottom, you see here, the one on the left is simpler, so that's tree A, but it results in 7 errors. Okay? The more complex tree, it's more complex, but it results in fewer errors. And the trick is this trade-off between complexity and the number of errors.
How do you know it creates that many errors?
That's given in the problem.
Okay.
Okay, so you've done this, and you notice that there are 4 errors that it doesn't quite classify everything. Right? So up here's that same typo again at the top. The total cost is the cost of the tree plus the cost of the data given the tree. And here's how we're going to calculate that cost using minimum description length. Okay? An internal node of the tree is encoded by the idea of the splitting attribute. And if there are m attributes at a particular decision node, the cost of encoding each attribute is log base 2 of m. in terms of bits. Similarly, leaves at the end are encoded using the ID of the class it is associated with, and if there are k classes, the cost of encoding a class is log base 2 of k. The cost of the entire tree is the cost of encoding all the nodes in the tree. To simplify, you can assume the total cost, adding up the cost of encoding each internal node and each leaf node. So that's just a simplification. And then now we're going to encode using the classification errors at the end. The one had 7, the other had 4. Each error is encoded by log base 2 of the number of bits, where n is the number of training instances. Okay, with me? So let's apply that to the problem that we have here. Ouch, I thought I had checked this. In fact, I have, but. So I'll read what should be up here. Cost for each internal node in the decision tree is log base 2, that's a 16. Yes, it is. Log base 2 of 16 bits, which ends up being 4 bits.
Makes sense.
Okay? The cost for each leaf node, and that should be a ceiling function here. It just doesn't display right here, but it's a ceiling of, so we've got how many classes? We had 3 classes. So the cost for each of the leaf nodes is the ceiling of log base 2 of 3, which is 2 bits. Pardon? It's 1 point something bits, and then the ceiling means round up, right? And the cost for each misclassification error is log base 2 of n. And so let's now calculate in general, and there's a piece that I have to discuss here, but the cost for tree A, okay, so going back to tree A, notice it has how many internal nodes? It has 2 and 3 classes, right? And the other one has 4 internal nodes and 5 classes in the end, right? One, you're counting the final at the very training instances there at the bottom. So when we do that, tree A, it's 2 nodes, log base 2 of 16 gives the 4, plus we had 3 classes times the 2, which log base 2 of 3. And remember, that's where that came from. And then 7 times log base 2 of n, where n is the total number of.
Where's the 7 coming from?
Where does that 7 come from? Okay, if you calculate, oh,
That's the number of errors.
that's the number of errors, right? Right. So 7 times 4 plus 3 times 7 plus, right, here's the 7 errors and 4 errors down below. A similar computation, we had 4 internal nodes and 5 classes at the very end. And here you had only 4 errors, so you're counting that less. And here, n is going to be your total number of attributes. So in this particular example, in fact, this is the largest, remember we had n was 16 attributes. So if I plug in 16 for n here, then tree A ends up being better than tree B. Turns out that as the number of attributes increases, it will switch. I think at 17 it actually switches. That tree B would be better. That has to do with, this one has the more errors. The A had more errors, so it's balancing the number of errors and the complexity. And I think that is it.